Hello all, welcome back to this online recording sessions in the series of deep learning lectures in data science. So in this lecture, we are going to see one of the deep learning concept, that is optimizers hill descent analog in 2 dimensionals. Okay, so we will see all the optimization algorithms or techniques, whatever you call, by taking the real life example. In contrast to that, we will be learning few concepts that are related to optimization. Okay, so let us see one by one. There are few lectures recorded by our faculties, so you can refer them. So the optimizers in 2D as well as 3D, it has been shown in this the above two links. You can refer that. But as of now, we will see first in 2D and then see 3D. Okay, so how the optimizers can be learned in contrast to the hill descent. Okay, what is this hill descent? Say suppose you take this hill. Okay, you take this hill. So imagine you are standing here. Okay, so your goal is to reach down. Okay, so your target is to reach down. So how do you travel this path? Okay, so how do you travel this path? So you need to travel this path irrespective of whatever the path may be. Okay, so the path may be with bumps, like some big stones will be there in your path, some valleys also will be there in the path. Okay, so how fast you could reach, okay, to the bottom of the hill is the example to be considered here. Okay, so if you are traveling by with the normal steps, okay, one foot, okay, it may take some time, but how far you will travel confidently or without any proper accident, okay, falling, collapsing on top of the hill. Okay, you need to reach here. Okay, so there are different cases, right? So one case may be you may be putting one step. Okay, in order to downfall, you may put single step by step and try to finish this and reach here. Okay, so another may be you may also jog, you may also run from the hill. Okay, it depend upon the surface. Okay, so if bumps are there, what you will do, you need to accelerate yourself and try to cross these bumps. Okay, and if the valleys are there, if valleys will be also there, no, in that case what you will do, so you need to overcome this valley and you need to travel this path. Okay, so on the whole, if you consider, there may be some obstacles while you are reaching at bottom of the hill. So depending upon the surface, you need to change your acceleration, you need to change your footsteps and need to travel, right? So in contrast to this, let us study this optimization technique. Okay, so that is what it is talking about. Imagine you are standing on the top of a mountain, high loss value. Okay, and your goal is to reach the lowest value. Okay, optimal weights. Okay, the way you descend the mountain represents how different optimizers behave. Okay, the way you descend, whether you move on single steps, whether you jog, whether you walk, whether you jump, whether you do whatever it is. Okay, whatever that task that you do to reach finally to the bottom. Okay, that all depends upon the behavior. Okay, how do optimists behave in this contrast of example? Yeah, so these are the key components in the hill descent analogy of learning optimization techniques. So the landscape can be considered to be as loss function. Okay, the mountain range represents the loss function surface. Okay, so landscape is the loss function. Okay, so gradient. Okay, uh, what is the gradient here? Okay, the slope direction. Okay, the slope direction, whether you are going to, you are taking right, you are taking left, or you are directly coming from the valley, or coming or crossing the bumps. Okay, like that. Okay, so the learning rate may be the step size. Okay, so learning rate, these are the terms that we will be using in our deep learning concept. Okay, but these are the concepts that we are trying to relate it to the this example. How do we travel on a from the top of the hill to the down? Okay, so the learning rate may be big steps. Okay, risk of overshooting. Okay, the risk may be very high when you are running from the slope, means it's difficult job, I can say. So it depends upon. Okay, so small learning rate means tiny steps, you can consider like that. Yeah, these are the examples that can be related. So what is learning rate can be contrasted with this example, uh, like step size. Okay, gradient can be considered like a slope direction. Okay, yeah. First one, okay, gradient descent. So what is gradient descent? Okay, so what is gradient descent? What is Adam optimizers? Okay, so all those can be seen. But let me talk about what is the optimization first. So we have input. Okay, so we get an output. Okay, output, input, output. So in this between we'll have hidden layers. Okay, we'll apply activation function, bias. Okay, all those things will be applied to get an output. Okay, so if this output is not accurate to the expected output, okay, so that means predicted output is not according to the actual output. In that case, what we will do, in that case we'll try to modify the weights. Okay, modify the weights. So first, before modifying it, we'll calculate the loss. Okay, with the help of loss function. Okay, with the help of loss functions we can calculate the loss. If loss is too high, what we'll do, we'll try to modify the weights using back propagation algorithm. That's what we have seen in previous sessions, right? So so if loss is too high, right, we need to modify the weights with the help of back propagation, right? Okay, so in this back propagation we use optimization. Okay, so in this optimization we'll modify the weights. Okay, during this the chain rule or memotization will happen during back propagation. Okay, so along with this chain rule and memotization, optimization need to be also be considered. Okay, while updating the weights. Okay, so through these algorithms, optimization algorithms only, we'll be modifying the weights. Okay, so there are various optimization techniques. Okay, there may be SGD, gradient descent, MSGD. Okay, mini batch stochastic gradient descent. SGD means stochastic gradient descent. So this is just gradient descent. Say suppose input means how if there is a data set, so the data set can be given in many ways. Okay, so the data set, so out of all the data set I can give only single input. I can give batch of inputs. Okay, that means I can group some inputs together from the data set and then I can give it that as an input, right? So I can give full data set also. Full input means full data set. Okay, so there may be possibilities of like this in giving input to get an output, right? So here if I give full data set, okay, so entire data set is considered to be as gradient descent. Stochastic gradient descent, okay, is a single point. If you give single point from our data set and try to predict the output, single point in the sense it can be of single feature also. Okay, so in order to identify a cat, what are the features I have shared previously sessions? I have shared eyes, nose, ears. Okay, so all those are features, right, that will be given as a input. Okay, in order to predict the output. Okay, so instead of giving all the inputs together, we can give single input also. Okay, how the cat looks, if it has a mustaches like this, okay, I can say it is a cat. Okay, so by identifying some features directly, we can tell for some images. Okay, instead of taking two three features or 2-3 inputs, we can take one input also in some cases. Okay, in some cases we can directly take 1 or 2 inputs and we can predict the output also. Okay, in some cases we need many features in order to identify. Okay, like if I take similar objects like horse. Okay, white horse and red horse. In that case, what, both look like same. Okay, in order to differentiate both, I need to take more features which are more relevant to the one particular item and which are more relevant to the other particular item. Then I need to contrast between those two, and I need to identify which object is what, whether it is a male horse or female horse, or whether you call it as a white horse or a red horse. Okay, like that you can also consider. Okay, so on the whole, I'm trying to share that you can predict the output by taking single input or batch of inputs or full inputs. Okay, so if you take single input, then we call it as stochastic gradient descent. Okay, if you take entire inputs, we will call it as gradient descent. Okay, if you take batch, okay, if you take in batches input in batches, then we call it as mini batch stochastic gradient descent. Okay, so this is very, very important. Okay, these three techniques that can be used as an input to in order to predict the output. Okay, so now we will see here the optimization techniques, and few more in addition to these optimization techniques. Okay, we not only SGD, gradient descent, stochastic gradient, and mini batch stochastic gradient descent, we'll be also seeing into few more optimization techniques in contrast to this hill descent. Okay, hill descent example. Okay, so first one is we are taking gradient descent. Okay, so gradient descent, how we can consider in contrast to that our hill example, we can consider moving person moving directly downhill one small step at a time. Okay, by considering small steps. Okay, the user try to complete the destination from the hill and reaches here. Okay, so uses the gradient to update the position. So it uses the gradient to update the position. So there is a drawback also of this technique. It takes too long to reach. If you take single steps, it will take too much time to reach, right? So instead of that, I can jog, or instead of that, I can run in order to reach fast. Okay, so the disadvantage is it takes too long to reach the destination from hill to bottom. Okay, so this is the formula that we use to update the weights. Okay, the weight will be is equal to the previous weight minus the loss weight that we will be calculating, and update the weight in gradient descent. Yeah, next, momentum based optimizers. Okay, the momentum based optimizer is the runner with inertia. Okay, with some inertia, with some speed. Inertia in the sense with some speed. If I will run rather than walk, then how would I reach my destination of reaching from top to hill? I will be reaching somewhat faster than gradient descent, right? Yes, exactly the same. So in momentum based optimizer, we'll move downhill while remembering the past gradients. Okay, so by remembering the past gradients, say suppose while I am traveling, so I have traveled, with my consciousness. Okay, so if there is a some obstacle here, I need to be conscious how would I travel, and then take this as example and use it for further traveling. Okay, so if the situation is like this, I have traveled like this, no, so now also I need to travel like this. Okay, you could analyze like that, and you can travel by running. Okay, so faster on slopes and avoids getting stuck in small bumps. Okay, so it will be faster on slope, we can run faster on slope. But what if we stuck in bumps? Okay, big bumps. Okay, small big stones will be there, no, it's those are like nothing but a bumps. Okay, so what if there are small big stones on hill? Even if I run, what will I do? I'll directly collide with that bumps. Okay, so that is a drawback here. If I run too fast, I may collide with the bumps. Okay, so this is the formula for momentum based optimizer. Okay, so next, ADA grade. So what is the ADA grade? So this is the combination of gradient descent and momentum based optimization. Okay, so the adaptive hiker with adjustable steps. Okay, so here what I will do, so I will walk and I will run. Okay, previously in gradient descent I will just walk and try to reach. Whereas in momentum based, I'll try to run and I'll try to reach the bottom. Okay, so you have seen what are the drawbacks. If I travel by walk, I may reach, it may take too long to reach the destination. If I run, I may collide with the bumps or I may fall in the valleys. Okay, so that may be disadvantage if I directly run. So now what I am doing in ADA grade, so I will adjust. I will run as well as I will walk. Okay, so I will run when the slope is clear and I will walk. Okay, I will adjust my momentum. Okay, I will walk when there is bumps or valleys in my journey of reaching the bottom. Okay, so this is what the formula that we will use to update the weights. Okay, so here you can see, adjust the steps dynamically based on the terrain. Okay, larger steps in rare directions, smaller steps in frequently visited regions. Okay, okay, so whenever we have reached to frequently visited regions, then we can uh, take small steps. Okay, or whether there is obstacles in between us, we can take small steps. If there is no obstacle, we will directly increase our speed, that means running. Okay, so next, RMS prop. So RMS prop, what is RMS prop? It is similar to ADA grade. Okay, it is similar to ADA grade. What it is actually, so RMS prop is the smart tracker with learning strategy. Okay, with some strategy. Okay, so with how much speed, okay, should I maintain constant speed or should I increase the speed at some cases? Okay, so this is the parameter that I can consider in RMS prop. Okay, okay, so it is similar to ADA grade but smooths the step size over time. Okay, so handles deep value better than ADA grade. Okay, so if there is in deep value, it handles better than ADA grade. Okay, it is similar, but it performs better than ADA grade. RMS prop will perform better than ADA grade. Okay, so now you see, we are trying to improve the optimization techniques. So the algorithms which are evolving now from the starting, from the gradient descent, you can see the evaluation, the improvement that we have noticing. Okay, okay, so it fastens. Okay, with fastness we can complete our journey in reaching the bottom of the hill from the top. Okay, so this is the formula in order to update the weights. Okay, so how fast you update, okay, the weight, okay, during back propagation. Okay, yeah, next, Adam. So Adam optimization is the mostly used in nowadays. Okay, if you, out of all the algorithms or all the optimization technique, Adam is the one of the most optimization technique that we generally used in deep learning concept. Okay, so the expert mountaineer. Okay, here what is the smart trekker is very smart in trekking. Okay, okay, but here expert means he already knows, he has climbed many times, he has seen all the obstacles, he has seen all the ups and downs, so he has the entire view and perspective of this journey. Okay, so he knows what to do. Okay, so that's what we call it here as expert mountaineer. Adam is an like a expert mountaineer. Okay, so RMS prop is smart trekker. He accelerates whenever it need to be accelerated, he will accelerate, but he is an expert, he has a all planned thing. Okay, since he has experienced it many times. Okay, so it combines momentum, RMS prop. Okay, it combines both. RMS prop is third technique, right? Momentum based is second technique. Okay, so it combines both, so that it will be fast, adaptive and efficient. Okay, so by this way we can move quickly and adjust speed based on the terrain. Okay, yeah, so this is the formula for Adam optimizer. Okay, so the final thoughts that we can take from the here from Adam optimizer is, these are the final thoughts. So if you're training a deep network, Adam is the best choice out of all the 5 optimization technique. Adam is the best choice. Okay, because it is an expert mountaineer, it knows. Okay, it has all the things from loss function calculation. See, it knows it knows entire process of learning rate or entire process of deep learning process. Okay, so that way we call it as expert maintainer or expert optimizer. Okay, it tunes according to the, or it adjusts according to the situation. Okay, so for smaller problems, SGD with momentum works well. Okay, so here we are trying to see which optimization technique to use when. So for smaller problems, we can use stochastic gradient descent with momentum. That works better. If you have sparse data, you can try ADA or RMS prop. Okay, you can try if it is sparse or dense. There are two types of data: sparse data, dense data. Okay, if it is sparse data, you can try with ADA or RMS prop. Okay, yeah, here is the summary. SGD, so is a careful hiker. It is simple and stable, but it is slow in deep values. Okay, so momentum, with momentum, it the runner tries to with a small inertia. Here the advantage is it is faster, but small bumps. Okay, faster, avoid small bumps. It tries to avoid small bumps. Okay, it takes another path. It will not cross the path. It tries to take different paths. Okay, while running only. Okay, can overshoot. The problem is the overshooting. Okay, next, ADA grade. So what is ADA grade? Hiker adjusts the steps. Okay, it adjusts the steps. Okay, it's good for sparse data, but steps shrink too much. Okay, so these are the just a summary of what we have seen before. Okay, next, RMS prop. RMS prop is a smart tracker, handles valley well. If there are valleys are there, it handles well. It is sensitive to the tuning. Okay, next, Adam optimizers. It's an expert maintainer. It is fast and adaptive and more memory, but the disadvantage is more memory usage if you use Adam optimizer. Okay, yeah, this is the overall diagrammatic representation. You can see SGD blue color, stochastic gradient descent. Okay, it is like a zigzag, 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 zig. Okay, when I am trying to show from far off, it may appear like a straight line, but it is trying to go zigzag. Then momentum is faster. Okay, so you can see, okay, it is moving after. You can consider the intervals. Okay, so this interval, you see the speed, with how much speed the user is trying to travel. Okay, so here the speed is more, that's why it's covered more distance. So next, Adam fast and smooth. Okay, you can see here with constant speed. Okay, you can see here. Okay, so this is the start point from where it's starting and trying to reach here. Okay, so this is a pictorial representation in 2D if you represent all the optimization techniques. Okay, so if you, this can be also seen in 3D representations. You can use these links. Okay, you can use these links and try to see the entire 3D. Okay, 3D optimizations, how it will be visualized in 3D format. Okay, so previously you have seen in 2D, so 3D also similar to that, concepts are same, but you can see here. Okay, so in this links or whatever I have shared, you can use that and go through if you want to study more about this concept. Okay, optimizers. Okay, so that's it for this sessions. Okay, so thank you for listening this session or giving this opportunity. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.